First, I would like to thank the organizers for giving me the possibility to come here. My name is Sebastinao Pilati, and I work at ICTP in Trieste. Today, I will tell you something about our recent research in the context of ultracold atoms. In particular, we will consider a system of cold atoms in so-called optical lattices. These are systems that in the recent years has been used somehow to play with Hubbard physics. So somehow they have been seen as a realization of the Hubbard model. But what we have been doing recently is to try to study and consider the systems in a slightly more flexible way. Okay. Here you see the list of collaborators which have been involved in this project. We have Tuan Nguyen. She's a PhD student at CISA. Then we have Matthias Troyer and a PhD student Ilya Thinchenko and Pingyan Ma from ETH. And we also collaborated with Professor Shidai from the Chinese Academy of Science. Okay, so probably you already know that playing with ultracold atoms, one can realize a large variety of situations where quantum coherence and correlations play an important role. These systems are very versatile, and so much that it has been proposed to try to use them to implement so-called digital quantum computers. And I have to say that before coming to this program, I used to believe that this project was too ambitious, and maybe it was a good idea to be, to be sold to politicians. But I used to think that classical computers would always have been faster and more powerful. But here we have learned that simulating on classical computers 10 non-interacting electrons in 2D is still a big challenge. So it might be that indeed we have to wait that people realize digital quantum computers, and maybe we will be able to do quantum simulations more easily. But okay, what I will talk about instead is inspired by a much less ambitious idea, and it is the idea to use ultracold atoms as analog quantum emulator. So what is a quantum emulator? I think yesterday we saw an example presented by Professor Bulgac. So the idea is that you have a physical system, a quantum system, which you are interested in, and it is very difficult to simulate. Maybe you don't know an exact theory, or maybe there are several theories which give different results. And then you ask the experimentalist to realize a system in the lab which behaves exactly as the physical system you are interested in. Okay? And so then hopefully the experimentalist will give you the answer. Okay? And I think this is, it's still quite ambitious, because maybe you cannot realize really all quantum systems that you might want to study. But I think that if also theoreticians do some work and learn how to develop theories which mimics the system of ultracold atoms, then maybe we will learn something which can be used also in different situations. Okay, so our research is mostly in the field of, say, condensed matter physics. And in particular, so we would like to use ultracold atoms to emulate the behavior of electrons in solids. Okay? And we are particularly interested in so-called strongly correlated materials. Okay? Typically materials which contain transition metals. The systems are particularly interesting because they show a plethora of fascinating and also useful phenomena. Strange insulating phases, quantum magnetism, you have giant magnetic resistance, and probably the most interesting phenomenon is high temperature superconductivity. Okay. The big problem is that in these materials you have electrons which are strongly correlated, and we don't have exact and reliable theory to predict their properties. Okay. So just to give you an idea, you might have a solid like this, and And you know that in a solid, the typical distance between atoms is 0.1 nanometer. And what we would like to do is to use instead dilute atomic gases to emulate the behavior of this system, which might look strange because in this system we have much lower densities. Okay. So in these systems here, our elementary objects are the atoms, while of course in the solid state you are mostly interested in the behavior of electrons, and in particular on the behavior of the valence electrons, which move in the electric field created by the ionic crystal. Okay? So what we want to have is that also our atoms move in a periodic field. Okay? And this can be created using so-called optical lattices. Okay? This is a very well-established experimental technique where you shine pairs of counterpropagating laser beams. They form standing waves. And the atoms, when they move in these laser fields, they experience a force which is proportional to the gradient of the square of the electric field. Okay? So they experience a periodic potential. Okay? The periodicity of this periodic potential is just half of the wavelength of the laser. So by changing the laser, you can change the periodicity. And the intensity is just proportional to the intensity of the laser. So for the experimentalist, it is very easy to realize situations where the periodic potential is weak or zero, or it's very, very intense. Okay. Okay. Another handle that the experimentalist can use is the so-called flashback resonance. And this is a technique that can be used to change the strength of the interaction between the atoms. Okay. This was already described by Professor Burkhardt. And with this technique, essentially, you can manipulate the value of the scattering length by tuning a magnetic field. Okay? And you can create two different situations. One is where the interaction is attractive. So here you can, for example, cool an atomic gas where the magnetic field is this value. And so you have a negative scattering length. Okay? So it means that you have attraction between the atoms. And by tuning the magnetic field close to the resonance, you can make the attraction stronger and stronger. Nothing happens. Okay? What happens is that at the unitarity, you have an interaction which is just strong enough to create two particle bound states. Okay? Nothing explodes. You just have two particle bound states. And if you go on the other side, adiabatically, then you create molecules. Okay? And you have a Bose-Einstein condensate of molecules. What I will discuss today is instead the physics that you can realize if you are in this situation, if you are in the so-called upper branch of the flashback resonance. Okay? So here, if you cool a gas in this situation, you have a small and positive scattering length. Okay? So you have repulsion between the atoms. And then if you tune the magnetic field close to the resonance, you can increase the strength of the repulsive interaction. Okay? So here we have a repulsive interaction. And as long as you have a collision between only two atoms, okay, these atoms will never decay to the ground state, okay, for energy conservation. So if the sample is dilute enough, you can hope to realize rather strong repulsive interaction. Okay? But this stability, you have stability only in the case that the system is sufficiently dilute. Okay? So unfortunately, if you have also three body recombinations or higher body interactions, it can happen that actually the particles fall to the true ground state. Okay? So there is experimentally, there's a difficulty. It is not possible really to go till unitarity and realize extremely strong repulsive interactions. And also theoretically, you have a challenge because essentially what you are asked to describe is a system which is not really in its thermodynamic equilibrium. Okay. I will not go much more into detail of this problem. If you are interested, you can ask me. Okay, so in the first part of this presentation, we'll mostly talk about bosonic systems. Okay. First, because for theoreticians and for Monte Carlo people, they are easy to study. And also because we want to see whether we can actually find agreement between quantum Monte Carlo and the experiments. And then in the second part, we'll say something about what we can do instead of for fermions. So if you have a Bose gas, and a repulsive Bose gas in an optical lattice, you can essentially realize the physics of the transition from a superfluid to a Mott insulator. Okay? If you have weak interaction and this periodic potential is not very deep, then you can imagine that at sufficiently low temperature, particles will hop, will form a long-range order, and then you have a superfluid. Okay? But then if you can cap the interaction, you can actually go to a situation where the hopping is strongly inhibited, is not exactly zero, okay? And you go into the Mott insulating phase. So the Mott insulator is a phase which has no long-range order, it's an insulator, but you still have a small amount of hopping, but this hopping is strongly correlated, and so you don't have conduction. Okay, so the minimal model that can be used and has been used extensively to describe this kind of physics is the single band Bose-Hubbard model. Okay? This is a model which is defined on a discrete lattice. Okay? So you imagine that the particles can move on the nodes of a discrete lattice. And you have two parameters. One is the hopping energy, which describes how easily the particles can hop around, and the interaction parameter, which tells you what is the energy that you pay when you have two or more bosons on the same lattice site. Okay? But this model is reliable only if the periodic potential is very, very intense. Okay? Quantitatively, if the intensity is much larger than the so-called recoil energy. And it's also only reliable if the interaction is very, very weak. Okay? Which means if the S-wave scattering length, A, is much smaller than the periodicity of the optical of the periodic potential. And I will say a little bit more about these approximations and how reliable they are. Okay? But okay, if you trust this model, then you expect to see a phase diagram of this type. Okay? Here you have the chemical potential, and here you have the hopping energy J in units of the interaction strength U. Okay? And this phase diagram, you have here a superfluid, and in these lobes you have the so-called Mott insulator, okay, where the density is commensurate with the lattice. So you have on average, you have an integer number of bosons per well. Okay? For example, here you have 1, here you have 2, and here you have 3. Okay? And experimentally, essentially, this phase diagram can be observed. Okay? So what you see here are results obtained in the group of Marcus Greiner at Harvard. And here what you see is an image of a two-dimensional Bose gas in an optical lattice. So you take really an image of this two-dimensional system from above. And in this system, the average density is not homogeneous because you also have an harmonic confinement. Okay? So the density is higher in the center and goes to 0 in the tails. Okay? And what you can see is what you can measure experimentally is whether in the wells of the potential you have an odd or an even number of bosons. Okay? So here, for example, you would have a Mott insulating phase with 3 bosons per lattice site. Here you have 2, here 1, and here 0. Okay? So essentially, observing the image of the system, looking from the center to the going towards the tails, is like going from high density to low density in this phase diagram, and you cross several phases. Okay, so I mentioned a minute ago that what the minimal model to describe the system is the single-band Bose-Hubbard model. But how do you actually go from the physical system, which is in a continuum and has a periodic potential, to a single-band model defined on a discrete lattice? Okay, here I will be very brief, but I just want to give you the idea. You can start from this conventional Hamiltonian written in second quantization language. And the key idea is that you can take your field operator and expand it on the basis of so-called Wannier functions. Okay? The Wannier functions are a complete basis set. You can derive them once you have the block functions of your periodic potential, and you have one Wannier function per well. Okay? And in each well, you have one Wannier function per band, per block band. Okay? And so in principle, if you do an exotic expansion, you would have a huge number of interaction parameters, okay? And just obtain them by taking this expansion inside here. So you will have a huge number of parameters parameterized by 8 indices, okay? 4 are lattices indices, and the other 4 are band indices, okay? And the conventional approximation is to throw away all of them apart one, okay? The one is where all of the indices all of the lattice indices are the same, and all of the block indices correspond to the lowest band, so they are 0, say. And then you solve this integral by placing a delta function inside the integral, okay? This has nothing to do with what is called Fermi-Huang pseudopotential in scattering theory, okay? Because actually, if you really had the short-range interaction, it would be completely wrong to neglect the interaction parameters where the block indices are not the same, okay? So this approximation of throwing away all higher block bands apart the single one, the lowest one, is correspond to what in scattering theory is called first Born approximation. So in principle, it might be an extremely crude approximation. Okay. So let me summarize what are the possible problems with the single band Hubbard model. Well, the first problem, as we said, it is reliable only if the periodic potential is extremely large. Okay. And we want to go beyond that. So we want to be able to consider also weak optical lattices, especially because experimentally you have several advantages in doing experiment in the regime of a shallow optical lattice. You neglect all of the virtual excitations to higher bands due to the interaction, which are very strong when you're dealing with short-range interaction. Okay. Remember that single band models were introduced in solid-state physics, and the underlying idea is that the Coulomb interaction is long-range, so it doesn't couple strongly different bands. While here we are dealing with short-range interactions. And then there are many other terms which are neglected. One important is called density-assist hopping. Okay. And there is one more fundamental reason to go beyond a single band model, and it is due to a claim which was made by Phil Anderson, this paper in 2009. And essentially, Anderson claims that bosonic systems at 0 temperature cannot be in an insulating phase. Okay. He says that at a sufficiently low temperature, bosonic system must have a finite condensate fraction. Okay. And of course, one could argue against the claim made by Anderson by citing all of the exact quantum Monte Carlo simulations which have been done for the single band Bose-Hubbard model. Okay? The single band Bose-Hubbard model, people have already seen clearly quantum phase transition from a superfluid to a Mott insulator. But here's an argument against that. It is very easy, and it goes like this. So what is actually a Mott insulator? Suppose that we go deep into the Mott insulating phase. Okay, in this phase, you can imagine that you have one boson per well. Okay? So one boson occupying each Vanier function. But the Vanier function is this red one, something like this. It looks like a kind of Gaussian, but it has wiggles in the tails. Okay? So it goes negative. And it has to have a negative part because different Vanier functions are orthogonal. Okay, so then if you build a many-body wave function with this orbital, which is not positive definite, you will obtain a many-body wave function which is not positive definite. And this is supposed to be the ground state of a bosonic system. And we know that bosonic system at 0 temperature should not have nodes.
Just a question. That just has to do with the basis that you choose. I mean, I don't see the argument. And also, I was going to say, you can cite other Anderson papers that say the opposite, too.
Okay, I cite this.
For instance, when people do this diffusion calculations, is there any way in which they try to sort of enforce the exchange among the different wells? I mean, because it may just be that, I mean, by ergodicity, it's very hard to see the
Yeah, you can do all types of swaps and permutations. Yeah.
They do.
Yeah.
Yeah,
No,
when we do the path intervals, and we try to make these ring polymers that stretch out across the box.
Yes.
And we find that they have an exponentially
Well,
small
if you
weight.
do that way, no, because you mentioned diffusion. I mean, diffusion Monte Carlo. I mean,
Right.
it's a little.
But I mean, we
Yeah.
actually looked and saw that the longer you make the exchanges, the smaller the weight is.
Yes,
It
no,
goes
exactly,
exponentially
yes.
to zero.
All right.
So I think Anderson's argument was that there's going to be exchanges between neighboring sites. And
Yep.
that's of course true, but that doesn't, just because there are exchanges doesn't mean that you can get long range
Yeah.
coherence.
I'm not.
You get short range coherence, but not long range.
Yeah, I'm not arguing in favor of Anderson. Indeed, I will show results which go against that. But this argument, the first part of his argument is rigorous. So you cannot take a single band Bose-Hubbard model and claim that the Mott insulator that you see must exist in the real physical world, because the wave function that you have is not positive definite.
What if you took positive only one-eighth function? I mean, these are.
Yeah. Then you have okay. That's what we will do
they're
next.
not exactly one-eighth. I mean, I guess that might not be the definition, but you could take a localized basis on the sites which are positive.
And you want to have them orthogonal, so they.
But what if you relax that criteria?
Yeah, we will do next.
You
Okay.
can put zero, then outside. You see, they'll be discontinuous, so you can make a function which goes from zero where the potential is maximum to maximum, then to zero where the potential is maximum again, and they'll be orthogonal by definition.
Yeah, that's not what the Bose-Hubbard model is. Bose-Hubbard model is derived using this. Okay. Maybe you can define another complete set of orthogonal bases, but I don't know any. So far, people have used vanilla
If
function.
you do the quantum Monte Carlo with the regular dispersion, you'll put the potential, you see the
We do-
oscillating potential. and
That's
so
what
on.
we do next.
What's the result?
That's what we see next.
Okay, so can you go directly there so
Yeah.
we don't spend time on discussions?
Yeah, no, you spend time. I was fast, you have spent time. Okay, so the Hamiltonian that we simulate is this. It's a very easy, conventional, continuous space Hamiltonian. So we have a periodic potential, which is the sum of three orthogonal periodic potentials. They are signed to the second power. And for the interaction, we use a very simple and crude model, which is the hard sphere interaction. Okay? So this is a crude approximation of how atoms interact, but this is better than the first Born approximation, which is used to derive
What's the radius?
the radius is equal to the S-wave scattering length, which we will
But
tune.
it's much smaller than the lattice constant.
It is smaller, but also not so small. So we will consider different values. Okay, we see that. Okay, so the computational method that we use is the ground state path integral Monte Carlo, usually called PICS. So here, I think that here you recognize essentially the data structure that you have in this method. Okay, so the idea is that at the extremes you have a triwave function, variational ansatz that you invent here and there. And then if your propagation in imaginary time is long enough, here and here, then here you should have the true ground state. Okay? And this method is extremely powerful. It works extremely well in a large variety of situations. But here we might have a problem, okay? Because what we want to do is to cross a quantum phase transition. Okay? And in the vicinity of a quantum phase transition, you can expect that you have correlations in imaginary time which scales with the correlations in real space. Okay? And the correlation in real space diverge at the quantum critical point.
You could also, this may be saying exactly the same thing, but those psi t's essentially carry the phase. And for example, you could have superfluid or non-superfluid. If you take a superfluid psi t,
It's difficult.
as beta goes to infinity, it's always going to be superfluid except at beta equals infinity.
Exactly.
Yeah.
Okay, so we want to have the flexibility to have psi t's, which are either superfluid or
Yeah.
perfectly insulating or whatever. How do we do that? It's next. So the idea here is to hybridize the method, so to have a method which works in partly in continuous space.
Is it three-dimensional?
It's three-dimensional, yeah.
Three-dimensional.
But it takes advantage of what we know from the physics of discrete lattice models. Okay? So what we do is to introduce a fictitious discrete lattice. So this is just a fictitious lattice, not the real system. It's just something which we introduced to help the computations. And we introduce a basis of localized orbitals, something which look like the Wannier function, but they are not really Wannier function. They're Gaussians, for example. Okay, and they're positive definite. Okay. And then for each particle in the system, we will have a coordinate in real space, but we also associate to that a pseudo coordinate on this lattice. Okay. And then if you work, if you imagine that you're working on a discrete lattice, then you know how to describe a good wave function, which can describe both a superfluid phase but also an insulating phase. And this is so-called bosonic Gutzwiller wave function. Okay? So this is essentially what in other fields is called Jastrow function, but it is defined using discrete lattice coordinates. And this is by far the simplest form of the Gutzwiller wave function. So here we have correlations only when the two particles are on the lattice side. Okay. And this is a variational parameter that you can tune and decide how easily two or more particles can occupy the same orbital. Okay. Then, of course, for each lattice configuration L, you can imagine to write down the continuous space wave function. Is just the product of the orbitals corresponding to the different particles. But then, of course, you have to take into account all possible lattice configurations. Okay, and this is a sum of a huge number of terms, of course. Okay, because if you have n particles in n lattice sites, you can imagine that you have to sum n to the n possibilities. Okay. This is not impossible because we do Monte Carlo. So the idea is just to sample these lattice configurations together with continuous space integration. Okay. So instead of doing just a many-body, an integral in many variable, we do an integral in many variable and also a discrete sum over a huge number of configurations. Okay, that's it. So the idea is to put together pieces coming from discrete lattice models and continuous space Monte Carlo methods. Okay, it is maybe interesting to see what you get with this type of wave function represented in real space in two limits. One limit when you take this variational parameter gamma equal to 0, then you have a very simple wave function with a one-body term, which is a block function with 0 quasi-momentum, so a periodic modulation, and a Jastrow term, which we also include. While if you go to gamma equal to infinity, you get the so-called permanent wave function. Okay? So this is the wave function that one might imagine to describe a possible supersolid phase. You have bosons which are localized on the sides of a lattice, but you still take into account all possible permutations between the bosons. So it is it preserves bosonic symmetry. Okay. And typically, what you get for the density profiles are something like this.
It wouldn't necessarily be a supersolid.
No, not necessarily. No, yeah.
It would be just a proper bosonic wave.
Yeah,
function.
proper bosonic wave function, which okay, that's what you would use if you believe that there must be.
What would be super solid in this case? It's a solid. Why do you call it super solid?
If these orbitals are very wide, you might imagine that there is still off-diagonal long-range order. We don't know whether this phase exists, but if it exists, then you should introduce a wave function which describes a solid but still preserves the bosonic symmetry. Okay, so you should still treat particles as bosons instead of as a distinguishable particle. Okay. And so what we measure to individuate where the transition from superfluid to insulator is let me call it condensate fraction. Is the asymptotic value of the one-body density matrix. It is not really the condensate fraction, it is non-homogeneous system, but it is a good order parameter which can be used to distinguish a superfluid from an insulator. And here you have some results at density 1. Say on average we have one boson per well. We fix the ratio of the scattering length to the lattice spacing. In this case it is 0.3. Okay, and then we vary the intensity of the periodic potential. Okay, and you see that this condensate fraction goes down At some point, it reaches 0. And to be sure that it goes exactly to 0, and we don't have just a crossover, which was what Anderson claimed, we performed some finite size scaling analysis in the vicinity of this critical point. Okay? So here we plot the condensate fraction versus the size of the system for different values of the intensity of the optical lattice. And you see that in the vicinity of the critical point, you approach the power law behavior that you expect at this quantum phase transition. Okay. So far, so good. So again, let's go back to experiment and see what they can measure experimentally about this transition. And here I will show some result obtained in Innsbruck in the group of Hans-Christoph Nagel. In this case, they can essentially measure the condensate fraction by measuring the momentum distribution, which you see here. And they measure that by taking an image of the gas after a free expansion. Okay? So they removed optical lattices and all confinement potentials. They let the cloud expand and take an image. And this image gives information about the momentum distribution that you had before expansion. Okay. And and they can, of course, modulate, for example, the optical lattice intensity, the intensity of the periodic potential, and see how the width of this peak changes. Okay. Now, as long as you have quantum coherence and long-range order, the width of the peak should not change. And that's what you see here. Okay. The quantity plotted here is the width.
The confining potential.
Sorry?
The confining potential, harmonic confining potential.
Yes, there is an. Yeah.
That one doesn't influence the width?
Very little, very little.
Well, you can say by how much, you see, because one can calculate that, right? That induces an uncertainty in momentum, inverse proportion to the size of the potential well. So how that compares with that?
We performed simulations in a system which on average is homogeneous. We use periodic.
Experiment.
Yeah.
So,
I mean, experimentally, you have that wedding cake structure, right? So you could be just observing superfluidity on the surface of the wedding cake, right?
There's a different experiment. So they have a large Mott insulator with one particle per well in the center. And of course, in the tail, then you have, well, in the tail, you have a normal phase because the density becomes very low.
Yeah, but you have a big edge between that n=1 and the vacuum. You have a big
well,
surface.
if the condensate fraction is small, you might not see in that experiment either because the error, its experimental resolution is not enough. So I don't think that's a solid argument.
What, my argument?
Yeah, looking at the experiment.
Yeah.
Yeah, because of that.
What we found when we're doing these things is that the width, you know, the wedding cake, the superfluidity or the condensate can penetrate quite a bit in, I mean, the surface is pretty fuzzy, in other words, of the wedding cake.
Okay, my understanding of this experiment is that as long as in the center you have some long-range order, then the width should not change. Of course, within some experimental resolution. So, of course, you see that this width is constant, but I mean, there's some wiggles. But there is a clear signal. So when you reach a critical point, then it starts moving dramatically. Okay. So in this experiment, what they did is to measure this critical point where you have this change of behavior, and to repeat the experiment by changing the S-wave scattering length. Okay. And you see how the curve changes. That's, of course, a way to estimate the critical point, but one might do better. So let's see how we compare with the experiment. So we can draw a tentative phase diagram. So here you have a zero temperature phase diagram as a function of the intensity of the periodic potential and the value of the S-wave scattering length divided by the periodicity of the periodic potential. And please notice that the scale on the horizontal axis is logarithmic. So we are in the simulations, we consider a very wide range of values of scattering length. Those which are relevant for cold atoms are only the one at the left of, say, this point. Okay? Beyond that, the hardcore approximation for the interaction is no longer reliable. Okay, so our results are the red dots. Okay. And the gray curve over here is the result that you would obtain by considering the single band Bose-Hubbard model. Okay. And you see that strangely, despite of the approximations that are involved when you derive the single band Bose-Hubbard model, the difference is not very large. It's quite small and kind of constant as a function of the strength of the interaction. Okay. The experimental results are the black dots here. Okay. So they seem to fall pretty well on the theoretical core.
What temperature were those?
Experiment or
Yeah.
simulation at 0 temperature?
Yeah,
Speaks.
yeah.
The temperature.
Were they around the TC or?
No, much below TC. Much below TC. Yeah. And okay, so seems nice. There is a pretty good agreement. Then, from the theoretical point of view, it could be also nice to say something about what could happen in this regime. Okay, so here we go to a regime where the scattering length is very large. So we have a dense liquid of hard spheres, but with a periodic potential. Okay. This arrow here indicates the point where hard sphere would freeze at 0 temperature. Okay, it was calculated a long time ago by Professor Carlos. Here I'm plotting a recent result which has been slightly improved by Rotta and Giorgini. Okay, and I think it will be very interesting to try to understand what could happen in this regime. Okay, now here the physics is different. So here we have a quantum phase transition, which is of second order, where you go from a superfluid to a Mott insulator. The Mott insulator has the symmetry of the optical lattice, okay, which is a simple cubic optical lattice. While we know that here on the horizontal axis we have a first order phase transition, and you go to a ground state where the hard sphere bosons will be in a FCC crystal. So we have no idea how one could connect this core with this point. So here this is just. Pardon?
The difference between the FCC and your simple cubic.
Yeah.
It's got to you're going to have to make V0 very small in
Yep.
order to not favor the
Mhm.
simple cubic. So it
Totally
probably
agree.
just a little tiny point down there. Where
Probably yes.
Yeah.
There's also the point that this transition is of second order type,
Right.
and this is first order. So, okay. Okay, then we extended the study to finite temperatures. And what we calculated here is using path integral Monte Carlo at finite temperature is the critical temperature for the transition from the normal phase at high temperature to the superfluid phase at low temperature. And we did that as a function of the strength of the interaction and for this different intensity of the periodic potential. So if you set the V0 to 0, you just have an interacting Bose gas in a homogeneous configuration. And then here you have the result which was obtained already a few years ago. And you see this intriguing effect that a weak repulsive interaction increases the critical temperature for the superfluid transition. Okay. And in this situation, you reach a maximum, and then TC instead starts going down. Okay. Now, if you add the periodic potential, okay, what you see is that, of course, the critical temperature of the ideal gas, okay, for A equal to 0 is lower, but the interaction plays a stronger role. So the increase of TC is faster here than here. Okay. And also the maximum is at a weaker scattering length compared to what you have in free space. So somehow it seems that the periodic potential has the effect of making the role of interactions more important. Okay.
Can I ask a question?
Yeah.
In the case of V0, it's 0.
Mhm.
Why do you have a dependence on D?
Oh, this is just, you can see it as a unit, of course. I could replot the data using NA cube or something.
Oh, because so it's simply you fill the space. So
Yeah, it's just a unit, just to compare with the other data.
I think you can, well,
Yeah.
you can think of this scattering length as renormalizing V0. So
Yeah.
as it goes up, it's basically lowering the effective barrier. It's as simple as that.
no, my question was different.
Yeah, yeah.
V0 is
I'm not-
exactly 0. What happens when I have dependence on D?
Yeah. And okay, so also here you have an interesting regime. So here you see that TC starts going down, and this black arrow here is the critical point where you have the quantum phase transition from superfluid to Mott insulator. Okay, that's what we obtain with the zero temperature technique. And here you have a regime which is very interesting, but it's a big challenge for simulations. Okay, so here we are in the vicinity of a quantum critical point. You are at finite but low temperature, and you have a problem of a critical slowing down in the simulations. So I think this is a big challenge for quantum Monte Carlo, which we should try to face in the future. Okay. So now let me go briefly to fermions. So now we want to consider a repulsive fermionic system. Okay, so we imagine that we have a kind of spin up and spin down particles. Okay, and that we can manipulate the strength of the repulsive interaction between the two components. Okay. And this system, one could expect to have the so-called Stoner instability, which I will explain here using a very, very naive description. So the key idea is that if you have a strong repulsive interaction between the two components, at some point the system will prefer to form ferromagnetic polarized domains with up and down. Even though this will cost some kinetic energy, but you will have a reduction of the interaction energy, because for short range interaction, as wave scattering is inhibited by the Pauli exclusion principle. Okay, and this is a minimal model which was introduced by Stoner to try to explain itinerant ferromagnetism. Okay, and okay, so at first this instability was estimated to be at this value of the interaction parameter by Stoner, and in later years it was refined by going beyond mean field theory and even doing quantum Monte Carlo. Okay. Now there were experiments done at MIT in the group of Wolfgang Ketterle, who tried to essentially implement an experiment where this instability could be observed. Okay. At first they claimed also that they did see Stoner instability, but this claim was recently withdrawn.
Can I ask?
Yep.
See, when you do the quantum Monte Carlo calculation,
yep,
do you observe domain of the formation there?
If you typically what we try to do is to use is to force the system to be in a homogeneous phase with no domains. Okay.
But if you do that, then you bias the
no. What we do is equivalent to say a Maxwell construction. So we determine the equation of state, zero temperature, as a function of the interaction parameter, KFA, and the spin polarization.
No, I understand, but in that case, you'll have to determine the surface tension. See, because if you have domain formation, you see, and then the shape of the domain, the size of the domain, and so on, you see, it's important.
Yeah, no,
I don't know, you see how you can do this accurately in quantum Monte Carlo. That's my question.
You can use a triable function, which is designed. Okay, I should say something more about what the triable function is. By the way, you can do a diffusion Monte Carlo where your wave function is forced to be the one of a system without domains. Okay, so you are estimating the equation of state of the system.
So you simply separate the system in two parts. And
yeah,
those together.
if you want, yes. That's
you put the planar surface separation, right?
Something like that.
Yeah.
Okay.
Yeah.
Okay. Problem with the experiment is that here you see that essentially to see this Stoner instability, you have to go to pretty large value of the repulsive interaction. We saw before that you might have instabilities, and for example, in this particular experiment, they have estimated that they can go up to values of the interaction parameter, which is something like 0.25. Okay. So way too small to see itinerant ferromagnetism. So the idea that one might have, again, is to introduce an optical lattice and see whether this favors or not the ferromagnetic transition. Okay? We saw before that the effect of interaction, if you have a periodic potential, is stronger. Okay? Now, if you have a periodic potential, you might imagine that you have a different type of magnetic phases. You might have a ferromagnetic phase, which in this type of system where the number of spin up and spin down particles is conserved will appear as a different domains. Okay, but if you are at the right density, you might also have some antiferrometric ordering. Now here we are dealing with fermions in weak periodic potentials, and so.
Excuse me.
Yep.
How do you avoid the formation of dimers in this case?
Which kind of dimers? Okay.
You have a bound state between the spin up and
Yeah,
spin
yeah.
down existing, you know, the lower.
Yes, yes, yes. There are
You
different.
have to inhibit that both
Yeah.
experimentally
Yeah.
and theoretically too.
Yeah.
Theoretically probably it's easier, but experimentally it's a
No,
problem, I believe.
It's a problem experimentally. It's a problem also theoretically. There are
That's
different.
how you do it.
Yeah, the result slightly depends on how you do it, and there are different procedures to do that. And the one which I will consider here is very crude. Is that instead of taking a true a potential which really represents a flashback resonance, we take a purely repulsive hardcore potential.
That, experimentally, you see, I'm concerned. You see how you
Experiment, yeah.
do this.
Yeah, yeah. No, experiment.
That I think it will be the real challenge.
Experimentally, they have been okay. In this experiment, what they see is indeed that they cannot go to sufficiently strong interaction, so they have the problem that you mentioned. And there have been, and there are many ideas, many proposals on how to force the system to be stable for longer times. And probably the most interesting is to use narrow flashback resonances. Okay. With narrow flashback resonances, the rate of three-body recombination is extremely suppressed. And indeed, in Innsbruck, in the group of Rudy Grimm, they already performed experiments with two species gas. So they had the lithium and potassium with a narrow flashback resonance. And in that case, you can follow the upper branch essentially through unitarity. Okay. So here you see that we have this problem of doing some predictions for interacting fermions in periodic potentials. Okay.
So,
Yep.
question, when you, theoretically, when you calculate this, how does the size of the hard sphere compare to the size of the modulator?
Oh, you will see later. Yeah. We will see the later the exact values.
Well, I'm worried if you make the size of the hard sphere bigger, well, that's
No, it's always small.
much smaller. That's the Hubbard model, right?
In some with the approximation that we mentioned before, yes.
So we have, there's predictions in the Hubbard model.
Yeah. So again, the procedure to map the system to the Hubbard model contains a lot of approximation. One is the first point approximation, which is even worse than taking a hardcore. And then, yes, of course, in some regime you might believe in the Hubbard model and use the. I mean, there are some approximation, so some prediction for the Hubbard model, but this is a repulsive Hubbard model.
Yeah.
And I think that the ground state phase diagram of the repulsive Hubbard model is still not known. Or do you have it? Maybe. I think it's a big challenge for theory, and actually that's one of the motivation that the experimentalists have to implement the system. They want to get the phase diagram of the repulsive Hubbard model. Okay, but here we want to work with weak optical lattices, where the Hubbard model is not a good description, for several reasons. One is experimental. So in the experiments, they have the problem of thermalization. They need to reach extremely low temperature, and this is difficult if the optical lattice is very deep, because particles don't hop very much, and they don't thermalize after evaporative cooling. So this is a regime which might have some advantages, but you need some theories, okay? So you need some theory for interacting fermions in periodic potentials. And of course, the first idea that you can have is to use Kohn Sham density functional theory. Okay, so it was already introduced yesterday. I don't need to go much into details. I just want to
Popple didn't get for DFT.
Sorry?
Popple didn't get the Nobel Prize for DFT.
Okay, the mistake here.
It's only Kohn.
Only Kohn.
Popple did for something else.
Gaussians.
Yes, exactly.
I guess Gauss was dead, but.
But it says,
I'm sorry.
It says Kohn Sham, it says Kohn Sham, you see, and Popple there.
Yeah,
I
yeah.
think, you see, Popple shouldn't be there.
I
think it was
apologize.
just Gaussians.
Yeah, correct.
Yeah.
Popple is only for Gaussians. Correct.
Defining model chemistry.
Yeah.
Okay. Sorry for the mistake. And okay, so the key idea of DFT is that you can dramatically simplify the many-body problem, and instead of having the problem to determine a many-body wave function, essentially you just need to find a density profile. Okay, so you go to a problem with 3 n variables to a problem with 3 variables. Okay. Yep.
Except you need the mapping.
Yeah, exactly.
Which is a function in a many-dimensional space.
Yeah.
So.
Yeah. Thank you for anticipating the next slide.
Really a simplification.
We'll see. Okay, it's a simplification. It's a dramatic simplification in the sense that people
when
are.
you make dramatic approximations, it's a dramatic simplification.
I totally agree. So we might. I am also very happy to insult the people that use DFT. The problem is that they are much more than us, so we should be careful because.
But they're not here, so we can insult them.
Okay. Well, okay. So here I found an analysis of the number of kilo papers published per year using DFT. So of course we might make jokes about them, but we might also think about the fact that there are many real problems, especially in material science and in quantum chemistry, really important problems that all scientists should try to solve. And apparently currently the standard theoretical tool to tackle those problems is density functional theory and not quantum Monte Carlo. So maybe it's our fault.
The QMC is in the kernel.
It's in the kernel, so I will mention that. Thank you. Okay, so you see you have a method which is very widely used, but it contains dramatic approximation. So can we do something about that?
You know, Betty said you use the method of successful approximations.
Yeah.
In DFT, it's a successful approximation.
Is it what?
Successful approximation. This is according to Betty.
I missed that word.
Hans Betty said that he's using the method of successful approximation.
Oh.
And DFT, it's one of those.
Oh, okay.
Okay.
Mm-hmm. Okay, so as Professor Seppeli mentioned, actually quantum Monte Carlo is in the kernel of the methods based on density functional theory, because in DFT essentially you have to construct a functional, which in principle we don't know what it is. People make this kind of guess, where you have a kinetic energy term, an external potential, a kind of mean field term. But the interesting physics goes inside this exchange correlation function, which is unknown. And one approximation which is found to be good, it's called the local density approximation, even though it might be more profound than that. Well, here the idea is that you take this exchange correlation energy and you obtain it as an integral of the exchange correlation energy of a homogeneous electron gas at the density that you have in that particular point. And this quantity was calculated by Professor Seppeli many years ago. So here the idea that we had was just try to do something similar for repulsive atomic gases in optical lattices and see what comes out. Okay. And so we have two motivations. One is to have some type of prediction for atoms in weak optical lattices, okay, where there are so far no predictions because people mostly use the Hubbard model, which is only reliable in deep optical lattices. And also we would like to understand how one might try to go beyond this local density approximation, which works, is extremely successful in many cases, but it also dramatically fails in very important situations. There is a huge number of methods that one could use to go beyond the local density approximation. Here I put a very incomplete list of methods which are being used. And the problem is that there is no systematic way to go beyond LDA. So when LDA fails, people don't know exactly what to do. And the approach is very much empirical. And the comment that I heard in one, when I talked to the, when I went to some conference of, with people doing DFT calculations is that you can always find a functional that gives the result that you want. So what you...
How do you know when your calculation has failed?
Yeah, that's the point. So we want to know where and when and why these approximations fail. And the idea that we have is that, okay, we might try to compare them against a physical system which is tunable. So with the system with cold atoms can be done strongly or weakly interacting and also almost homogeneous or very highly inhomogeneous. So to us, it looked like the best place where you can test these approximations and try to learn somehow from nature. Okay, so we performed some Kohn Sham-DFT calculations for repulsive Fermi gases and optical lattices. Here you see some phase diagrams, and they're given as a function of the density and the interaction parameter. And what you see here is that if you have an extremely weak optical lattice, just 0.5 recoil energy, the ferromagnetic phase appears also only here. But if you make the optical lattice slightly more intense, then this ferromagnetic transition appears at much weaker interaction. Okay? And here the effect is even stronger. So somehow it seems that adding an optical lattice strongly favors the ferromagnetic transition. So it might be that, okay, this is a much weaker interaction strength than what you need here, so it might be reached in the experiments. Okay, so we also performed some simulation at half filling. Okay, so here you see a phase diagram as a function of interaction strength and intensity of the optical lattice. And we see that DFT predicts indeed that there should be an anti-ferromagnetic phase here. Okay. Now, we don't know how much we can trust these phase diagrams. Okay, so they have been obtained using local spin density approximation. Okay. What we hope is that experimentalists will give the answer and explain how intense can the optical lattice be before LDA breaks down. We still don't know. Do you have the answer? We don't know.
So there was no QMC in this?
Okay, the QMC is the functional. Okay. The functional for the homogeneous system. Okay.
So the functional is for hard spheres.
For hard spheres, yep.
In a box, calculated in a box.
Mm-hmm.
And this is LDA.
Mm-hmm. LDA with the periodic potential.
Right.
LSDA, local spin density approximation. And okay, so
for electrons, I'm not sure how well that does for ferromagnetism.
Not very well, because it goes back to the earlier question, right? You can't really model the strong interaction regime, right? The answer is not reliable. The hot sphere size is too big compared to the size of the modulation.
Yeah, yes.
Mean field things tend to exaggerate the tendency of correlation. Right? The only way to do that is to separate electrons.
Yeah, this is true, but the problem is even worse if you were using the Hubbard model. That's the point.
Yeah, so maybe one question one could ask is, with the Hubbard model, right, how well?
I'm saying that the Hubbard model is even a worse approximation than the hardcore. Okay. With the Hubbard model, you're not using the zero range Fermi one to the potential.
You mean worse approximation
than the hard sphere model.
For experiments.
Yeah.
Yeah.
Okay.
But this is not, you can't, with the hot spheres, you're not really modeling the experimental interaction, right?
Even worse with the Hubbard model. Okay.
That may be true. The Hubbard model is really not designed to do that.
Okay, so I mean, if you have a better description, then I mean.
Or you could do QMC directly on this model.
Right.
Which models? Yeah, that's what you have next.
Yeah.
Okay. So of course we cannot do exact QMC. We have fixed node approximation. The hope is that the experimentalists will draw the exact phase diagram. But to start with, we also did some QMC with this exact model. And so here you see a phase diagram at density which is 0.75. So you have slightly less, so less than 1 fermion per well. It's given as a function of the intensity of the periodic potential and the scattering length. And here you see 3 phases: the trivial paramagnetic phase. There is a region where the system is partially ferromagnetic, and then the region where it is fully polarized. And so the QMC result are the blue one here and the black one here. Okay. And so you see that also in QMC, it seems that adding a periodic potential favors ferromagnetism.
Where is the LDA, LSDA prediction?
LDA is this one, so you should compare these triangles with this, and the dashed curve with this.
Okay, so it is true that LSDA
Fails.
apparently seems to stress the
Yeah.
the
Yeah.
tendency
So
for
here there is a yeah.
a general property of any mean field approach. I mean, if you have a mean field approach in a repulsive potential, you come up with ferromagnets everywhere.
I partially agree. It is still true that Kohn Sham-DFT functional theory is not exactly a mean field theory. It's kind of. It takes into account somehow of correlation effect.
It's better than Artifault.
Exactly, that's
okay, but
No, I'm not here to sell you DFT. DFT is already sold much more than quantum Monte Carlo. So I'm trying to see whether quantum.
Doesn't mean that it's better, but.
Yeah, okay. I'm trying to see whether with QMC we can say something about.
Junk food is usually much better sold than gourmet food.
Okay. Okay. Well, we can say this here. And, okay, so that's it. Let me just conclude by summarizing. I just want to summarize a few just intuitive ideas. I hope that I have convinced you that ultracold atoms in optical lattices are the ideal playground to play with strong correlations. And I also hope that I convinced you that one can perform simulations of atoms in optical lattices by doing continuous space simulations. So it's not that you can only do Hubbard physics with that. From the methodological point of view, I want to suggest the idea of trying to combine the QMC method that I usually used for a lattice model with those which are used for a continuous space model. Okay? Typically, with the lattice model, we can see all types of interesting physics, fascinating phase transitions, but they're typically just toy models. While if you play with a continuous space Hamiltonian, well, typically you might have a more realistic description of a physical system, but it is much more difficult to see interesting physics. Okay. I think that on the long term we should try to combine the two approaches and put the two techniques together. Okay. So I also hope that I convinced you that we might try to use QMC in non-homogeneous system to test the DFT method and possibly improve the functionals beyond what is known so far. Okay. And then maybe I would also like to conclude by suggesting a few challenges for QMC method that I see. Of course, beyond the same problem, we all agree that QMC guys should try to tackle and possibly solve the same problem. There might be others, and I think we should conclude at the end this program with a list of challenges and milestones that we want to reach in the next 10 years. A few of them might be, I suggest, well, I think we should try to learn how to simulate strongly correlated systems, but using realistic Hamiltonians, not just toy models. I think that a big problem that we have not discussed so far, I hope we will, is about disorder, in particular many-body localization. And again, maybe we could also try to combine quantum Monte Carlo method, so the good food with some junk food, so DFT, and see if together we can do a good meal for more people. Thank you very much for your attention.
I was too harsh. I was too harsh.
It's better than gourmet food?
You'll pay for that. You'll pay for that.
It's recorded. We remove.
There is a student in Illinois that's doing a disorder problem in conjunction with the experiment. Experimental group. I mean, of course, there are a lot of disorder problems, but we're focusing on trying to model a certain experiment. But we're doing bosons because we can do the same number of bosons as in experiments. So that way, fermions is always in the future, but.
You're simulating disorder Bose-Hubbard model, I guess.
Yeah.
Okay.
Although we think sometimes we should go back to the continuum models, but right now we're doing the Hubbard model. Yeah.
Same number of bosons as an experiment. That's impressive.
It's around 200,000 bosons. Yeah. Well, one of the things, of course, the experiments, they don't know how many. They don't know every, you know,
Well,
they
you
do a
could arrange
shot,
that
and
too.
every time it's 200,000 plus or minus
Yeah.
5%, right? And the temperature, they don't know either. So there's a little bit of,
Well,
So
you
you
could
need
do the
double
calculation
blind-
with
double
a
blind data.
undefined number of particles. too.
what's that?
You could let the number of particles vary and fluctuate the temperature. And you could
It's true.
have the same ignorance that the experimenters did.
More questions? No, thank you.
Let's take a